Hello and welcome to this clip on applied calculation questions. So they may require several things of you, such as balancing equations, applying mole ratios, and knowing what mole equation to use and when. So when you first look at them, they might seem challenging, but there is a knack to this, and that's to get started. Find something that will let you in. So your way in is what to look out for. Once you've found your way in, the rest of it often falls into place. So I hope perhaps this clip might help you a little bit to pick up some strategies to assist you if you come across one of these questions in your paper. So looking at this one, it gives you quite a lot of space and what appears like not very much information. Obviously there's quite a lot of data in the middle sentence. Well, the first piece of information you can read straight off is the MR of CXHYOZ is 150 grams per mole, because it tells you that the molecular ion peak is 150. So if you look carefully, it shouldn't be difficult to find the data that you need to work out the moles of everything by using moles equals mass over MR. So if we take a moment, you can see where I found the 5.119 and the 1.5754 for carbon dioxide and water respectively. All I've done is I've gone to a periodic table to work out the MR of carbon dioxide is 44 and the MR of water is 18. So that gives me 0.116 moles of CO2, 0.0875 moles of H2O, and because I've already been told what the MR effectively of CXHYOZ is, I can divide my mass of my sample of compound E, 4.362 grams, divided by 150 to make 0.029 moles. So once we've got the number of moles of carbon dioxide that are made when 0.029 moles of compound E is burned, and also the moles of water that are made when 0.029 moles of compound E are burned, you can work out the mole ratio of C to H in compound E, or CXHY. So we're trying to work out what X and Y are here at this particular point. So I'm going to bring the page down to try and finish off the calculation for you. I'm just highlighting for illustrative purposes why I've multiplied 0.0875 times 2. If you look at 0.0875, it represents the number of moles of water. Water contains 2 hydrogens, so we want the moles of hydrogen atoms, not the moles of water. So anyway, that gives us 4 to 6. So to get the proportion of oxygen that's left, you take the 4 to 6 ratio and you multiply them up by the atomic masses, and then you take that away from the MR that you've already worked out. So the proportion of carbon is 4 times 12 out of the 150 grams per mole. The proportion of hydrogen is 6 times 1 out of the 150 grams per mole. So that gives us 96. To work out how many oxygens fit into 96, you divide that by 16, which gives us 6. So now we can apportion how many atoms of each element are in the CXHYOZ. So bring down the page slightly to give us room to do that. That gives us C4H6O6. So let's now have a look at the mark scheme to see how close we were. So we worked out the number of moles of carbon dioxide and water, got a mark each for them. We worked out the number of moles we had in our 4.362 gram sample of our compound was 0.0291. We divided by that each of our moles of carbon and hydrogen to get the ratio of 4 to 6. By difference we worked out how much oxygen we had, and then that led us to the molecular formula. So we got that mark and we got 5 in total. This one's, although it looks difficult because it's talking about large amounts like tons, all you have to remember is tons are no different to grams. 1 ton is 1,000,000 grams, as you can see further down. So you can use that to scale down to grams and then do your mole calculations. But the first thing to do is to look at the first part of the question. Obviously it says construct a balanced equation for the formation of nitrogen monoxide from ammonia. In other words, that part of the flow chart. Now balancing this using the traditional method that you worked on at the beginning of your AS course, or the first year course, and maybe at the end of your GCSE course, is going to be quite difficult. It's going to take quite a long time. Now, if you're reading this or listening to this as an A2 student and you've done redox titrations and redox to A2, you may well have come across balancing using oxidation numbers. That's a far easier way to do it. So I'm going to take you through how to do that instead. So let's start with nitrogen. Nitrogen is -3 in ammonia because H is always +1, isn't it? So 3 H's will be +3 in total, 3 lots of +1. So going from -3 to +2. So it's clear nitrogen's been oxidized, and in that process 5 electrons have been lost because the oxidation number has gone from -3 to +2. It's increased by 5. Now oxygen has been reduced. It ended up in two places. It's ended up in nitrogen monoxide and it's ended up in water. But the oxidation state of oxygen in nitrogen monoxide and in water is -2. So in each case an oxygen atom has gained 2 electrons. But be careful here, because it's O2, that means there are 2 oxygen atoms within O2. Each one has gained 2 electrons. There's a total of 4 electrons gained. So for the oxidation and the reduction to support each other here in terms of electron transfer, 5 electrons lost times 4 gives you 20. 4 electrons gained times 5 gives you 20. Right, so what loses 5 electrons? It's nitrogen. So multiply the nitrogen containing species times 4. That means 20 electrons have now been lost. What gains the electrons? It's oxygen. How many times? 5. So multiply oxygen times 5. Now, to balance the water, where does the hydrogen come from? It's only one place, it's the ammonia. How many hydrogens are there in 4 ammonias? There are 12. So this must mean there's now 6 waters on the right hand side. Now, although at first this might seem a slightly roundabout way of balancing an equation, I suggest you try and do the same balancing without using oxidation numbers. It will take a very long time. Considering that's 1 mark, that would have been a mark you might have had to ditch and just move on. If you come across an equation that's difficult or looks difficult, try the oxidation number method. Trust me, it always works out. So now let's go to the next one. Assuming that 1 mole of NH3 produces 1 mole of nitric acid, and that all the NH3 is converted, calculate the mass of NH3 that's required to meet the annual demand for HNO3 in the UK. So the first thing I've done is gone back to the beginning part of the question, where it tells me that there's 700,000 tonnes of nitric acid. To do any mole calculations, I've got to convert that to grams. So I've used the fact that 1 tonne is 10 to the 6 grams, a million grams in other words, to work out that the mass of HNO3 that's needed annually in the UK is 7 times 10 to the power of 11 grams. So I've worked out that I've got 1.11 times 10 to the power of 10 moles of HNO3 needed per annum. That's what P.A. stands for, per year, per annum. I've written down the MR of HNO3. So always quote the MR, really important. There's a very strong chance that that will be one of the marks. So, if we know that it's a 1-to-1 mole ratio, we also know that it's 1.11 times 10 to the power of 10 moles of NH3. So that now means we can work out the mass of NH3. So let's quote the MR for NH3. So multiplying the MR times the moles, that gives us 1.887 times 10 to the power of 11 grams of NH3. I'm just going to bring the page down a little bit so I can put the equivalent value in tonnes. Now the question doesn't actually tell you which units you need to put it in, so I put it down both just to cover myself. It took 2 extra seconds to do that final calculation, so it's a good investment of time. So now let's have a look at the mark scheme on this one. So we got our first mark. As you can see, that probably would have been quite difficult to work out without using oxidation numbers. So always remember, if you come across a difficult looking balancing equations question, it's only not going to be 1 mark, so make it easy on yourself, use oxidation numbers. So in the next part, we quoted the MR, we gave the correct mass, so that got us our 2 marks there. So this one is quite applied because it talks about an innocuous enough reaction, hydrogen iodide gas being mixed with chlorine. But then it says 2 reactions take place forming different compounds of iodine, A and B. Compounds A and B contain I and Cl only. So there's no hydrogen and no oxygen in those particular compounds. So in the first reaction, compound A forms as a reddish-brown liquid, and compound A contains 78.15% of iodine by mass. So combining what's been highlighted and taking away 78.15 from 100, that means that compound A also has 21.85% by mass of chlorine. So this means I can work out the empirical formula of A using the percentage by mass that I've now calculated, divided by the relative atomic mass of the element I'm working it out for. So that gives me 78.15 over 126.9 for iodine, and 21.85 over 35.5 for chlorine. So a little tip there, never round relative atomic mass values. It might seem obvious just to take them out of the periodic table, but sometimes people round them up and round them down by mistake, thinking they're tidying up their maths, but in fact what they're doing is introducing error. So please remember never to do that. So I keep the 0.9, I don't call it 127, I don't call it 36. So 126.9 and 35.5. So in both cases I get 0.615, so it should be easy enough to deduce from that that the ratio of iodine to chlorine in A is 1 to 1. So for the equation for the reaction with hydrogen iodide with chlorine making A, remember, read what it says at the top of the question. So compound A is ICl, and you can make it 2 possible ways using that method, and I've put them both down just to be on the safe side. So the second one's slightly trickier in that it only gives you 467 grams per mole to the -1 as the MR. Okay, so one way around this is to look at which of the 2 elements, iodine or chlorine, has the greater mass. So obviously iodine has, because it's 126.9. So if you divide 467 by 126.9, you get 3.68 times. So there's a maximum of 3 iodine atoms that can be present. You can't have 3.68 iodine atoms, obviously. 4 iodine atoms would go over 467. So 3 lots of 126.9 give you 380.7. That gives 86.3 left out of your 467, which leaves room for only 2.43 chlorines. Now you can't obviously have 2.43 chlorines, so we're going to just have a think about this for a second. Instead of assuming 3 lots of iodine, assume 2. So this is like a stab in the dark, but it's an attempt to calculate this. So it's quite tricky, this bit, like we said earlier, but let's stick with it. 2 lots of 126.9 equals 253.8, using this new assumption. Take that away from 467 and you're left with a figure that can be divided by 35.5 to make 6 exactly. So that gives us I2Cl6. So that gives us one possibility as our equation. There is another possibility, just like there was another possibility for A, but I've now added in blue. Okay, so let's have a look and see how we did on the mark scheme. So we got our 1-to-1 ratio in the first instance and transferred that into ICl. We got our equation and we got I2Cl6, and we putting both of those equations in. That second one was quite difficult, so the advice there would be don't be afraid to try some trial and error. So in this case that would mean seeing how many times iodine and chlorine could fit into the MR of B. So let's have a look at summarising some of the strategies you might want to think about if you come across an applied calculation question like the ones we've looked at in this clip. So always look for what we call the starter marks. This gets you moving. It'll be quite easy to spot, and it'll be able to be done straight away just to get you up and running. If you come across a one-mark equation that appears more complicated than normal, and it seems like it's taking a lot of time to try and get that one mark, consider using the oxidation number method. Many complex equations can be balanced this way. So if you get unfamiliar units, such as tons, always remember to try and convert them back to the standard units before using your mole equations that you've remembered. If there's a conversion that's required that they wouldn't expect you to memorize or have to hand, they'll provide this for you so you can just put it into action. If you get given masses of carbon dioxide or water, usually you'll be given both, from combustion, then this information can be treated as information to work out carbon to hydrogen ratios in the original compound. It's just a mole calculation, moles equals mass over MR. And last of all, there's absolutely nothing wrong with using a little bit of deduction or trial and error. If you've managed to create some time elsewhere in the paper and you've got some time to do this, there's nothing wrong with doing it. Obviously, if you're short of time, don't sort of go down a pathway where you're not quite sure whether you're going to get the right answer. This is obviously time limited, but that would be something, a judgment call you'd have to make yourself in your paper. How far are you? How much have you done? How much time have you got left? So if you're coming back to a question because it seemed a bit tricky earlier and you've got a little bit of time left and everything else is taken care of, there's nothing wrong with doing a bit of deduction or trial and error. You'll not lose marks for trying something out. Okay, so hopefully you found this a reasonably useful clip to give you some ideas to get started with. If you do come across one of these questions, best of luck of course. In the meantime, if you are given homework or a piece of work to do and one of these questions pops up, then do bring it into one of us at college, have a chat in the subject extension, or maybe come and see your teacher and have a talk to them about it. But for now, thanks for your time and thanks for listening, and see you soon.